In the last several videos, we used the recursion tree method to solve a variety of recurrences generated from divide and conquer algorithms. For some of these recurrences, we saw that when we drew the recursion tree, the level sums did not change down the tree. For some other recurrences, we saw that the level sums formed a decreasing geometric series. And for some other recurrences, we saw that the level sums formed an increasing geometric series. So there were essentially three different types of recurrences. There were recurrences for which the level sums did not change down the tree. There were other recurrences for which the level sums formed either an increasing geometric series or a decreasing geometric series. We're now going to try and solve a generic recurrence equation of the form T of n equals a times T of n by b plus some function f of n. So A here is the number of subproblems into which the original problem of size n is broken down into, and each subproblem is an instance of the same type of problem but is of a smaller size. The size of each subproblem here is n by b, and f of n is the amount of effort in terms of time needed to combine the solutions to the different subproblems. So one can say that the values of a and b need to be positive, of course, because you cannot divide a problem into a negative number of subproblems or have a negatively sized subproblem. But more specifically, we can say that a is going to be some number greater than or equal to 1, because we need to divide the original problem into at least one subproblem. So the values of a in the examples we took were either 3 or 4. As for b, every subproblem needs to have a size that is some fraction of the original problem n. Some fraction of the original problem size n. So b needs to be a number greater than 1. So for some of the problems b was 2, some other examples had b equal to 3, and one of them had b equal to 4. And f of n was some function of n that was um, positive, of course. The range of the function was positive, and n being the size of the input, n is also going to be greater than or equal to 0. In fact, we bottomed out our recursion when we hit a subproblem size of 1. So we can assume that the size of the subproblems, n, is going to be uh, greater than or equal to 1. And the values of f of n will also be positive, because you need a positive amount of effort in order to combine the solutions to the various subproblems. So f of n will be greater than or equal to 0. So let's now use the recursion tree method, the same method that we've been using on these particular examples, to try to tackle this general recurrence. T of n equals a times T of n by b plus f of n. So let me write down the recurrence again. T of n is a times T of n by b plus f of n. And since we are not working with specific examples, we need to always keep in mind that a is greater than or equal to 1 and b is greater than 1 as we go through the calculations. So when we use the recursion tree method, we are going to have a single node to start with. That's T of n. In the next round, T of n will be replaced by the right hand side of this recurrence, depicted diagrammatically in this form. F of n will be at the top, and this node will have a children. Each of the children will be T of n by b. So I'm going to call this value a, which is the number of children each node is going to have, which is also the number of subproblems each larger problem is being broken down into. I'm going to call this a as the branching factor. Okay, so then in the next round, when we open up these nodes in turn, we will need to use the recurrence T of n by b equals, if we just substitute n by b throughout this recurrence, we get a times T of n by b square plus f of n by b. So in the next round, we will end up with a nodes at the first level, each of which will be f of n by b. And their children, so each of these nodes will have a children, and each child is going to be T of n by b square. We can continue this process on and on until our recursion bottoms out. That is, our subproblems reduce to a size of 1. So the final snapshot of the recursion tree is going to look like this. We're going to have f of n at the top. This is going to have a children, each being f of n by b. Each of these nodes is in turn going to have a children. Each child will be f of n by b square. And each of these nodes in turn will have a children, f of n by b cube, and so on. Until our recursion bottoms out at problems of size 1. So we'll have T of 1 at the very bottom, the bottommost level. So if we mark the level numbers, the root is at level 0. These A nodes are at level 1. These nodes are at level 2. These nodes are at level 3. The bottommost level is at level H for the height of the tree. And in general, at level I, we are going to have nodes with a cost of f of n divided by, you can see that the powers of b are increasing here. So at level I, we are going to have each node having a cost of f of n divided by b to the power I. What about the number of nodes at each level? At level 0 we have a single node. At level 1 we have A nodes. At level 2 we have A square nodes. Why? Because each of these A children, each of these A nodes has A children. So these are the A children of f of n. Each of these nodes, each of these A nodes is in turn going to have A children. So the total number of nodes at level 2 is going to be A square. Again at level 3 each of these nodes has a branching factor of A because we are dividing the original problem into A subproblems. So the number of nodes at level 3 will be A times the number of nodes at level 2. So the number of nodes at each level is going to go up by a factor of A. So at level I, we will have A to the power I nodes. And at level H, we will have A to the power H nodes. Let's now compute the level sums. At the topmost level, level 0, we have a single node with a cost of f of n. So our level sum will simply be f of n. At level 1, we have A nodes, each with a cost of f of n by b. And so our level sum is going to be A times f of n by b. At level 2, we have A square nodes, each with a cost of f of n by b square. And so our level sum is going to be A square times f of n divided by b square. At level 3, we have A cube nodes, each with a cost of f of n by b cube. And so we'll have A cube times f of n by b cube nodes. The level sum will be A cube times f of n by b cube. At level I, we have A to the power I nodes, each with a cost of f of n divided by b to the power I. So our level sum at level I will be A to the power I times f of n divided by b to the power I. At the very last level, level H, we will have A to the power H nodes, and the cost of each node will be t of 1, some constant. So we can express the running time t of n as the sum of all these level sums. So again we will write the last term separately, A to the power H times t of 1, and we'll group together the remaining H terms from level 0 to level H minus 1 into a summation I varying from 0 to H minus 1, A to the power I multiplied by f of n divided by b to the power I. Let's express H in terms of n. If you notice, as we create an additional level when expanding our recursion tree into this final form, when we created level I, our subproblem size was down to a size of n by b to the power I. So when we created level 1, we had subproblems of size n by b at level 1. When we created level 2, we had subproblems of size n by b square at level 2. So when we created level I, we would have had subproblems of size n by b to the power I at level I. And when we created level h, we would have had subproblems of size n by b to the power h at level h. Okay, so subproblem size at level h would have been n by b to the power h. So we would have had p of n by b to the power h when we created level h. But then level h is the bottommost level. This means n by b to the power h is 1. This means we can express the height of the tree in terms of n. It's going to be log of n to the base b. Because if b to the power h is n, then we can take log base b of both sides. So log base b of b to the power h is going to be h, and log base b of n is going to be this. So the height of the tree is log of n to the base b. If that's the case, then what is the value of a to the power h? A to the power h is the number of nodes at the bottommost level. So a to the power h is going to be a to the power log of n base b, which in turn is going to be, we can swap a and n here, n to the power log of a base b. N to the power log of a base b. So T of n can be written as n to the power log of a base b multiplied by T of 1 plus summation of I varying from 0 to h minus 1, where h is log of n base b, a to the power I multiplied by f of n divided by b to the power I. Now of course we don't have specific values of a and b, but in the examples that we saw, there were 3 different possible combinations of values of a and b and f of n. In some cases, this series turned out to be a decreasing geometric series. In some cases, this series turned out to be an increasing geometric series. And in some other cases, every term in this series was the same. So we could simply multiply we could simply take one of the terms and multiply it with h to get the value of this summation. So in the next video, we will look at 3 different conditions. Okay, what determines whether this summation is going to be a decreasing geometric series or an increasing geometric series, or just a constant number, just the same term appearing h times? Well, that's going to depend on values of a, b, and the function f of n, which is used to combine together the solutions to the subproblems. When each of these terms is the same, as we saw in a couple of examples, then the value of T of n was simply the value of any of these terms multiplied by the height of the tree, which is log n. So it was simply f of n times log n. Let me go back and show you an example. If you recall, For this particular example, t of n being 4 times t of n by 2 plus n square, we ended up with the same level sums at each level, n square, and the overall complexity of this algorithm was n square times log n, which was nothing but n square multiplied by the number of levels, which was log of n. So in the general case, the overall complexity is going to be f of n multiplied by log of n, because log of n is the height of the tree, log of n base b to be specific. When this summation, when all these terms form a decreasing geometric series, then we saw that the overall complexity of the algorithm, or the asymptotic complexity of t of n, was determined by the first term in the geometric series. And the first term here is f of n. The last term here is n to the power log of a base b multiplied by t of 1. So when these terms form a decreasing geometric series, you can expect that n to the power log of a base b is going to correspond to a smaller rate of growth than f of n, right? Because when this is a decreasing geometric series, it's f of n that's determining the overall asymptotic complexity. In which case, you will expect that the last term, which is n to the power log of a base b multiplied by t of 1, or a to the power h times t of 1, this term is going to be a lower order term compared to the very first term f of n. In the case where all these terms were constant, where we simply had to take any of these and multiply them by the log of n, you would have expected a to the power h times t of 1 to have the same rate of growth as any of these terms, including f of n. So in that case, you would have expected f of n and n to the power log of a base b to have the same rate of growth. And in the third case, where these level sums form an increasing geometric progression down the tree, you would expect the last term to be the dominant term. The first term is f of n, the last term is a to the power h times t of 1, which is n to the power log of a base b times t of 1. So you would expect this term, n to the power log of a base b times t of 1, to be dominant over f of n when this forms an increasing geometric series. Of course, t of 1 is constant, which means that if you compare n to the power log of a base b with f of n to the power log of a base b is going to be the dominant term. So there are going to be three cases. And those three cases are the outcome of comparing n to the power log of a base b with f of n. Either f of n could be dominant over n to the power log of a base b, or both of them could have the same rate of growth, the same asymptotic complexity, or n to the power log of a base b could be dominant over f of n. We're going to look at this more specifically in the next video, but I'm just trying to give an intuition here that depending on which of these three cases the specific values of a, b, and f of n lead to, we are going to end up with different kinds of series, either an increasing geometric series or a decreasing geometric series, or the same term appearing log of n times. And that's what generated the variety of examples that we saw, depending on which of the three cases were true. Sometimes f of n had the same complexity as n to the power log of a base b. Sometimes f of n was dominant over n to the power log of a base b, and at other times n to the power log of a base b was dominant over f of n. So having given this intuition, let's look at these three cases in detail starting from the next video.